The reaction of sodium and chlorine is a vigorous one. We use sand to protect the flask from excessive heat. Then, we fill the flask with chlorine gas. Next, we add sodium. And then a few drops of water to activate the reaction. The reaction produces sodium chloride. When sodium and chlorine react, the sodium transfers an electron to the chlorine, forming oppositely charged ions. Although the compound has no net charge, its component ions of opposite charge attract each other to form ionic bonds. In turn, these ions are attracted to others, and an ionic solid called a crystal lattice is created.
You can argue in the real world that nothing happens without money, like you need money to make transactions, to buy things, etc., etc. In science, the equivalent kind of somewhat negative view of the world is that you can't do anything without energy. So let's talk a little bit more here about those ionic bonds, those interactions between positives and negatives. And the fancy name for positive ions connecting to negative ions, the fancy name is called an electrostatic force. And you could see when sodium chloride was being made there that there was a lot of energy being given off. This is a very exothermic reaction, which means energy is given off, and that's basically like making money in the real world. If you can have an exothermic reaction, we're going to see that's a pretty good thing for most of science, and that's a conversation we're going to be developing over this whole Chem 221 through Chem 223 sequence. But for right now, just realize that when you have an ionic compound with positives, negatives going on in 3 dimensions, up, down, left, right, forward, backward, very strong forces. And the forces are called electrostatic forces, which means basically positive charges attracted to negative charges.
A crystal of potassium bromide has a distinctive shape with perpendicular edges. This shape directly reflects the arrangement of the ions in the crystal lattice. The compound is composed of alternating potassium ions and bromide ions.
Sometimes you can see in the real world, the macroscopic world on the left, what's happening on the atomic world there on the right. And those ionic compounds, potassium bromide, I believe in this case, very, very strong. So you can actually see the crystalline structure there on the left, which is kind of a cool thing. Ionic forces, or electrostatic forces, are very strong. There's a law called Coulombs Law, which tells chemists and scientists in general how strong the electrostatic forces are, because some forces are stronger than others. And it's important, I think, at this point to talk real briefly about Coulombs Law. Now, if you've taken physics, you will have seen something that looks like this. This is the official version of Coulomb's Law. And in Coulomb's Law, you calculate a force, and the force has so many newtons, a type of connection between them, and it's related to those things. We won't use this as an equation in chemistry. All right, we're not going to actually calculate newtons. We won't talk about the proportionality constants, that K and stuff like that. However, we can use Coulomb's law to kind of in a hand-waving way to tell how strong things are. The force, which is how strong the positive-negative charge is, has 2 pieces which are going to be really important to us. The top part of the equation is the number of positive and negative charges. So you can imagine that for something like sodium, chloride, you would have a positive 1, and you'd have one positive 1, and you'd also have one negative 1. So positive 1 times negative 1, basically a factor of 1, and that's pretty strong. However, if you have magnesium and oxygen, or oxide as magnesium oxide, you'd have a positive 2 and a negative 2, and 2 times 2 is a factor of 4. What that means for us here is that magnesium oxide, a lot stronger of a force than you have for sodium chloride. I like to think of it as handshakes. Each positive charge is like a handshake. I mentioned something about this earlier. So sodium chloride would be like a single handshake between a positive and a negative. Magnesium oxide with a positive 2, negative 2, that would be like a double handshake, and that's even stronger. But there's another factor we have to think about, and that's in the denominator of this equation, and that's the distance between the ions. Now, if you want to shake someone's hand and you're across the room from them, you can't shake their hands. Your hands aren't literally long enough to do it, all right? You have to be within a certain distance to make it happen. So as the distance between the positives and the negatives gets higher, or the distance gets farther from each other, then the force goes down too. There's like going to be some ideal distance that makes the forces happen. These little pictures right here show examples of this. First of all, this is a lithium ion and a fluoride ion. And when they come together, there's some idealized distance d between the radius, the middle of the lithium, and the central part of the fluoride. And as that part gets bigger and smaller, that's going to affect the bottom part of Coulombs law. Now, in part B over here, this is like a positive 1, negative 1 handshake, sodium and chloride, and that's pretty strong. But the one below it, this would be like magnesium oxide, a positive 2, negative 2, and that really makes it happen. So this part right here is important. As the ionic charges increase, the force of attraction increases as well, makes the charges stronger, and that's really important. Now, the far right side here shows the distance part. Here's a very small distance, and here's a very large distance. So let's consider the small distance like 2 people shaking hands, all right, and that's a good distance. But then if you increase the distance, like across a table or something, then it's kind of awkward to shake someone's hand. So the force is smaller as the distance increases. So this is the other important part here. As the distance increases, the force decreases. So these two parts, the parts right here at the bottom, are both going to be important in future discussions. As the charges, ion charges increase, the force of attraction increases. Also, as the distance increases, the force will decrease. And we're going to see lots of uses of this in the next several chapters. As the ion charge increases, the attractive force increases as well. So the first blank there, you would put in increases. Ion charges go up, the attractive force goes up. On the other hand, the second one, as the distance between the ions increases or gets bigger, the attractive force decreases. So it gets harder and harder to shake someone's hand as you're basically walking away from them. And we're going to use this in several upcoming discussions. Again, we are not going to actually use Coulomb's law for calculations. That's something that physics will do. But in chemistry, we'll use Coulomb's law to explain why some bonds are stronger and some are weaker. This is an example of 2 ionic compounds, and the first one is sodium chloride, which is positive 1, negative 1 interactions. It's a very strong bond. If you were going to melt table salt, you'd have to heat it up to more than 800 degrees Celsius. So very, very high. That's not an easy temperature to get to. Like most stoves certainly would go much less than that. You need some pretty special equipment. So sodium and chlorine atoms are holding on to each other really strong. And it's in 3 dimensions, forward, backwards, left, right, etc., etc. However, Magnesium oxide, +2, -2, you've got that double handshake going on, and it's much harder to break apart +2, -2 than it is +1, -1. So if you wanted to melt magnesium oxide, which is a way to see how strong it is, 2,800 degrees Celsius, a heck of a lot higher than sodium chloride. So this is not easy to melt. And what you're seeing here, the left-hand side is a +1, -1 sodium chloride handshake, and that's strong, but a +2, -2, that's an even stronger handshake, and that's going to be harder to break up. If we had a +3, -3 compound, that would be higher yet than 2,800 degrees, because that should be even stronger. And by the way, all of the atoms here are about the same size. At least sodium and magnesium are close, and chlorine and oxygen are close. We're going to talk more about sizes in a future lecture.